Just as with the vector algebra, as long as every expression to begin with makes sense for vectors, then the rules of differentiation will apply. The rules that you remember from calculus 1 still apply. So, for example, this one, as long as you realize that this is a vector function, parametric curve, and this is a numerical scalar function, then the product rule works out in exact same fashion. And in the meantime, you have a similar rule for the product rule for dot product rule. Okay, so that f of t dot g of t together they produce a scalar function, and if you differentiate that, everything the formulas are exactly the same. So that's pretty much it to begin with. The main rules with twice as many product rules, but it's still exactly the same. So if a calculus 1 student who walks into this room would not be probably surprised by these formulas. Okay, so the proofs are all can be done component-wise, but don't have to. So, for example, for the dot product probably, but for the product rule, the scalar product rule, if you prefer, then I just might refresh your memory of how the proof works out in calculus 1. You probably don't remember, but in case you do, so I take my difference quotient for this function over here. Okay. So what do I have? I have c of t plus h f of t. So we're just doing regular multiplication. Okay, the difference, the change of the location, if you like, and then I put in the middle, divided by the change of time. Okay, and then I have to work my way towards that expression on the left. So there is if anybody remembers how it is done. There's a trick here. How do you get you get 4 terms out of 2 terms, because every derivative is made of 2 terms, as you can see. This is the derivative. It has 2 terms. To have the answer with 2 derivatives, you'll have 4 terms. How? Well, you just add and subtract. Okay, so I will subtract. What do I want to subtract here? So I want to differentiate the first one. So I have ct f of t plus h. Okay, that is, I'm adding it, and then I'm subtracting this and adding that. So I'll have c of t f of t plus h. Okay, and then I still have the 4th term remaining. And this is a t over here. Okay, c of t f of t. Okay, and then it turns out that there are 2 lines. Each of these 2 lines are actually will converge towards the derivative that we care about. Let me demonstrate. So I will factor f of t plus h. I will factor f of t plus h over here with the first term. So it will be f of t plus h. And here what I have is c t plus h minus ct over h. Okay, that's the first term, the first 2 terms in my expression, and then followed by, this time I will factor out c of t, and I'm left with f of t plus h minus f of t over h. So that's one. Even the trick itself is exactly the same as in calculus 1. It looks, once again, it looks exactly like if we don't use any kind of arrows to indicate vectors to separate them for numbers, the proof is exactly the same. And what's the last step? If I take the limit of this with h going to 0, what am I getting? Where does this go? No, limit. It's I don't substitute, I take the limit. Naturally, if I substitute it every single time, you're going to have 0 with 0 indeterminate expression. But under the limit, what do I get?
Going to infinity?
No.
Because 0.
This is the change of c. Forget about everything else. We have a function c. It is c of t plus h minus c of t divided by h, increment of c over the increment of a of t. Where does that limit go? What's the limit of that?
The derivative of ct.
It is derivative of ct, that's right. Provided, of course, that the function is differentiable in the first place. But that's okay. So where does the second term go? F of t plus h. So if c is differentiable, then as a numerical function. What?
F of t.
F of t provided
F is differentiable? Or
F
continuous?
continuous sufficient. F is continuous. Okay, so nothing, no need to do anything with c of t here. And what's the last term?
Just F prime of t.
F prime of t. Once again, we have to require that F capital is differentiable. So, as you can see, differentiable requires continuity. So we actually need to only only differentiability of the two functions. All of these, by the way, all of the rules, just like in calculus 1, these are very abbreviated versions of those rules. They are just provided with formulas, nothing else. There is always the build-up of every formula. The conditions are always the same. If f and g are differentiable, then the sum is differentiable. If f is differentiable, then its multiple is differentiable. If, once again, those f and c are differentiable, then the product is also differentiable and so on. So as you can see, the requirements, they cannot be overlooked. So the two functions, if not differentiable, these limits simply do not exist, and the proof does not work out. But other than that, as you can see, that's where that formula of the product rule, that's where it comes from. The scalar product or otherwise, that's where it's come from. So it's just moving stuff around a little bit. Okay. So these are the two main rules. You could apply them very effectively. Say, let me actually apply this rule. For example, what if I want, I can easily modify some of the, well, how about we take the circle again, but this time we'll modify it. So I have my, say, P of t is t cosine t, t sine t. Well, first of all, can you tell what kind of curve this is? Let's say t larger than or equal to 0.
Is it a spiral?
It is a spiral, yeah. And you can see it because you can take t out, and then you have your circular motion is combined with the stretch. So you will rotate it as if nothing happens, but the rotation becomes bigger and bigger and bigger like this. So indeed, it is a spiral. Not you don't come back. You cannot come back because t grows. So t indicates your stretch and indicates your roughly the distance to the origin. So it's actually my picture is not right here because it actually starts at the origin and then starts to it starts at the origin like this and then continues to wrap around it like this. Okay, so we could easily differentiate it as it stands, but you can apply the product rule, or what did I call it, scalar product rule, with so p prime of t is, and then I just differentiate this as indicated with this being f. So I already know what this derivative is of sine cosine. So it will be 1 times f doesn't go anywhere. And the second term of the product rule will be t times the familiar derivative, negative sine t cosine t. Okay, so So I'm wondering, well, it's hard to tell what the meaning is, but if we already know what the curve is, then we just, all we can get, the best we can get from this is the actual derivative. So, so it is a bit quicker, I suppose. Okay, so let me, well, there's the fifth operation, which takes some time to remember, and that's the fifth operation is composition, and then for compositions we have the chain rule. Okay, so the rule of the chain rule of the derivative of the composition. Let me write out as the way we would state it in calculus 1. So say f of g prime of x is f prime of g of x times g prime of x. So in other words, you could say that we're talking about the derivative of the product, the derivative of the composition is equal to the product of the derivatives. Okay, so that's at least the initial point of view is this. So composition, and it turns into a product. Of course, this is not just the product of the derivative of f, because you have to compose it with g in order for the whole thing to make sense. But we could, let me also write the second version, which is slightly different. So let me write it this way, e dx f of g of x. So it's a function of x, and g is substituted into f. And then and the answer is f prime of g of x. So as you can see, g is substituted into the derivative of f, and then multiplied by the derivative of x. Okay, so that's another way to put it. Which one is more convenient? We'll see in a minute for our purpose now and for our purpose of parametric curves. But we have to go back to the discussion of what we can compose our parametric curve with, in order for it to make sense. And we also, you can compose it with a lot of things, but we want to compose with things that we already know, and we can compose it only with the things that we know how to differentiate. Which means that you cannot either compose a parametric curve with another parametric curve, which is impossible, or it is we compose it with the numerical function. So say t, say u here. U, one variable, then t, and then p. Okay, so parametric curve f here, and here's a g, numerical function. Okay, so once again, remember that was the example that we could compose parametric curve with a function of several variables. I don't know, h. Okay, with real value. Okay, but we just don't have discussed derivatives of these functions yet. Okay, so that's why we're not looking at this for the time being. Okay, so then we're left with numerical function followed by a parametric curve, and this is a vector or point in a multidimensional space. Okay, so then let's see if the formula makes sense. Well, certainly, well, to begin with, how about I just adjust my formula from calculus 1. So this is from calculus 1, those two formulas. And I'll just, to begin with, let me just, okay, what should be my variable? Looking at the diagram at the bottom, what's the variable? U. So g is a function of u, and then we have to replace the f lowercase with f uppercase. So this is still u, and we'll see if it makes sense. Okay, so this, well, I move that too, and I put a bunch of capital F's. F, 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 and F, and E. Okay, so let's see. Let's start. Let's take the last one. So we have a composition of F followed by G. This one. It starts with U. So the whole thing, this composed function made of two, is indeed a function of U, and we can differentiate. The result is, by the way, if I take now this as a whole, like this. This is my function that goes from U to P. It is a parametric curve. Okay, and what the meaning of G could be anything. If you look for some real life example of this, it would be, say, rescaling time, changing seconds to hours, or shifting, starting measuring time at 12 o'clock or at midnight. So these are simple examples of compositions with parametric curves that represent motion, and T is time. Then what could U be? It could be also time, just measured in a different way. Okay, so but the result is a new parametric curve. Okay, so and then we interested in that derivative of that parametric curve, and so that makes perfect sense. On the right, we are still in the same place. So the derivative of F, okay, so it's a parametric curve, so it certainly makes sense. It is, remember, the derivative of a parametric curve is also a parametric curve, all the same variable. Okay, so the outputs of that parametric curve are different, right? So the original parametric curve, for example, might be measured in feet, and its derivative with respect to time will be measured in feet per second. So the output will be measured in different units, but nonetheless, the input, these two are still a match, because the input of F prime is T. So this is still T. So that works out. And G prime of U is what is it? It's just a numerical function, so there was no trouble there as well. So the formula works out exactly the same way. The proof, I'm not going to do the proof, but I wanted to notice that the component-wise application would work just fine. You can prove it component-wise. So proof. Component-wise, if necessary. The example, you can certainly see where the product comes from. So if you don't want to examine the proof, actually, we certainly don't have time. You can think about where this multiplication comes from. So you have your F, your location, it's measured in time, T, and then you have computed its F prime, which is your velocity. And what happens if you rescale your time? For example, time goes faster or goes slower. How does it affect your new velocity, your new measured velocity with respect to this new way to measure time? Well, you multiply, right? So if you multiply time, if time goes twice as fast, well, the whole thing goes twice as fast, and vice versa. Okay, so that composition certainly will be helpful in the future. But let me go back to here. Okay, so the actual definition of the derivative rate of change, the geometric construction is, so that's the formula. In a box. This is the formula, the definition of the derivative of a curve. Okay, I want to take another look at the construction, the geometric construction that produces the same effect. So parametric curve, we sample it, we draw displacements. Okay, in green vectors. We bring then these vectors to start at the same point. Then we rescale it proportionally in such a way, because we have division by h. So this is division by h, and that makes it smaller or larger. It's not just we don't know whether it's larger or smaller. The question doesn't really make sense, because if we divide by h with h measured in time, so the units are entirely different, so you cannot compare them anyway. And then we take the limit. Okay, so the end result is a new parametric curve. Let me draw it for you. So in fact, we started with the parametric curve made of points, okay, and it ended up with a parametric curve made of vectors, but just as well we could put a curve and see what the endpoints of the difference quotients, rather the limits of derivatives, trace out. Okay, so these are the derivatives this time. So this is still displacements, but these are actual derivatives. Okay, at one point at a time. And so they're a bunch of vectors, but they are originated at the same point, and they actually trace a new parametric curve. Okay, so well. What about backwards now? We don't want to, like in calculus, we want to wait for 2 months and then start doing integration. Okay, so we got to go straight and look at what happens if we reverse this process. And certainly the easiest way to think about it is what is the meaning of the antiderivative of a function. Antiderivative or the indefinite integral, what's the meaning of it?
If you differentiate, you get your function.
You differentiate, you get back. So antiderivative. Okay, so then if I was, let me just point this out here. So how should I put it? G is an antiderivative. So we're now speaking of the whole function of f capital if g prime is equal to f. Okay, so that's the definition of antiderivative, and it literally reverses the effect of differentiation. There are many possible answers. We already saw examples of this, because if you're talking about g representing velocity and f representing location, this is the relation between them, but you could start at a different location and have the same velocity, right? So when you reverse that operation, you have ambiguous answer because of that. You can remember the calculus 1. All these are all, well, maybe not like exactly like that, but if you very carefully you draw the same curve. So starting at the say different locations, they will follow the same curve. If the curve is the same shape-wise, it will produce exactly the same derivative. So that's why it is ambiguous. But if you provide an initial condition, like with motion, if you know where you start, the initial condition plus the velocity, you know where you are, or you know your exact location at every moment in time. So to get to the actual computations, things are very similar to calculus 1. But let's quickly take a look at what happens with if we reverse this operation. If we reverse this operation, geometric computation of the differentiation. Okay, so suppose I have my parametric curve. Okay, so that's my parametric curve, which I call F. Did I call F? Okay, and yeah, and then so how do I anti-differentiate? I drew. I suppose I already have the version, and so I drew vectors. So I represent my parametric curve as vectors to begin with, unless it was already in the first place was given by vectors. So these are simply f prime. I'm sorry, f's. These are f's as they depend on time. So the time is not present here, but it could be say t equals 0, t equals 1, t equals 2, and so on. Okay. Then what I do is I once again I look at it. We are reversing the operation. So we are going. What's the next step? Dealing with h. So once again here we divided by h. We're going to multiply by h. So well, what I missed here failed to mention here, we first sample it. We first sample it. Okay, so sample, if you want to do the approximate computation first, you sample. You sample, and then you have a bunch of vectors, and then you take each of these vectors and multiply by h. So f prime of t gets multiplied by h. The result is pretty much the same thing. If I can try to do what I did last time. Okay. Okay, so which is rescales again. So the effect is rescale. How larger or bigger, we don't know. So this is gone. Okay, the curve is gone, and now these are, what are these? These are displacements now. So exactly the same as last time in reverse order. These displacements, and now what do I do with these? What do I do with these? Look at the picture. Moving backwards, we are here. Okay, we got the displacements. We're moving back. We arrange them head to toe, head to tail. Okay, so head to tail. It's a bit hard with these, are kind of a longish. So let me make this smaller, but roughly there seems to be slightly shorter and slightly turning like this. Okay, and then the end result is a new parametric curve already. So these are we trace the points. We trace the points. If we know the initial point again. So these are g of t, antiderivative of f of t. Okay, so that's how you sample it, and just as so you already have sampled points, it will be an approximation. If you might be satisfied with that. If you want a precise answer, what do? You let once again h go to 0. What's going to happen? These will be more and more frequent. Okay, the scale will be different. These will be shorter possibly, but together they will be just adding small. These will be shorter. Okay, so these will be shorter, and then as you're adding smaller and smaller pieces, the whole thing will converge to a curve. So at the end, you're going to have some kind of curve. Okay, so this is g of t. So this is g of t approximated. But if you take the limit, under the limit you will have actually a parametric curve, which is antiderivative. So that is describing pretty much what we're describing. On one hand, we're describing over there Riemann sum. So that each term over there is the Riemann sum. And I'm sorry, why do I have a prime here? There's no prime. Just f. Okay, so we take my value of my function multiplied by delta h, which is the increment of time. You can think of this also as if we're talking about motion, and h is the increment of time, and f of t is your velocity that you assume for that period of time is constant. That's why how far did you go? That's how far you go. Time, velocity times time, and then you add them all together, and then you know at every moment of time where you are located. So that's the approximation. And now computation-wise, just like with in calculus 1, some of the rules have and some do not have counterparts. So differentiation rules, you have a bunch of them, and then you don't have too many rules as far as integration is concerned. So you remember which ones have counterparts? For integration. So this is the rules of differentiation, rules of integration. Which one still available?
Sum and constant multiple.
They definitely these. The product rule there is kind of shaky. Sometimes some say that the integration by parts is in fact the product rule, but probably not. It follows from the product rule, but really does not look like the product rule. So it is integration will only have to begin with. Even though there's a fifth one, it is the composition, and it certainly works both ways. What's the counterpart of the chain rule in integration?
Substitution.
Integration by substitution. So that one is exactly right. So as we just saw, differentiation term by term, we have carried out a couple of times. Okay, so that there is really no challenge, and then there is also no challenge to do anti-differentiation as much as anti-differentiation is possible. It's always a challenge if the functions are complicated, but you can imagine that we can retrace these steps, no trouble, and just arrive to the just in the back where we started. So say. So if I want to integrate, say, sine cosine, indefinite integration. So this is an okay, kind of cumbersome, but okay notation. And then I apply the theorem about integration by component-wise. We didn't really state that one. So we have to sort of use the differentiation component-wise statement, reverse it to understand that we can also integrate component-wise. And component-wise, so literally split my integral sign between the two. And I have one big vector, which is just fine, as long as if we can, whether we finish this computation or not, we will have. Integral of sine negative cosine. Integral cosine is sine. Well, what's missing?
Plus C.
Plus C. Is this right? What?
We can pull out. Can we pull out the C?
We could, yes, but the yes, we could. In fact, we will, but I want to deal with this first. There's something wrong with this.
Is it that we're assuming it's the same C?
Right. It is a mistake. We integrated twice. We separated. Totally two dimensions, not related to each other. We integrate sine, we integrate cosine, we get one constant, we get another constant, have nothing whatsoever to do with each other. Okay. And then once we understand that, we can continue on and indeed pull out these constants out, pull out of the limit, as the idea is to make it as structured as possible, so we can see some kind of patterns. So in this particular case, it will be cosine t, sine t, something familiar, okay, and plus the vector of ck, where in that vector ck, both of the components are arbitrary. So these are both arbitrary. What does it say about the whole vector? Arbitrary components, arbitrary vector. So that's arbitrary vector, and you don't have to do anything with it. You can just so you can shorten the answer is like this. And you can even put C here if you really like letter C, which we do, I suppose, and just say, well, that's a vector rather than speak of a number. This time it's a vector. It's not the same C as we just had, but maybe I want to make that point. So we could, if we just ignore this part, then this is a fine answer, and which suggests that one thing, that we not only have to deal with the constant twice or thrice if you we're doing third dimension, and instead just say, well, there is always a vector to be added, an arbitrary constant vector. So it's exactly the same story as with anti-differentiation in dimension 1. You add a constant, except this time it's not going to be a number, it's going to be a vector. So every time it will look like this. And so in other words, what is the conclusion? Yeah, the conclusion is about two possible interderivatives, because with or without C, or with different values of C, it will produce different interderivatives, and they all differ by constant. Remember that result? So in other words, if you know your velocity every time every moment of time, and then you start at two different locations, they will trace out. You will trace out two exactly same curves. So same curve. not just the same curve. Remember, the parametric curves, their paths do not reflect the whole complexity of the situation. You will be, every moment of time, you will be separated by exact same vector. So every little, like this. So if the vector is this, C, that's the vector C that connects two initial conditions, then well, let's say we have two actually different people moving, what we would following the same plan of the velocities over time. That vector will reappear every time like this. Okay, so once again, the markings are when the two people are located at the same time. So that's the same time, same time, same time, same time. So the theorem that you might remember from Calculus 1 is, can you state it? The relevant theorem to summarize this situation that we just have learned.
We have, if f is a function, we have two antiderivatives, they differ by a constant.
Then they differ by a constant. So in other words, say f prime is equal to g prime, then f minus g is constant. It is exactly the same statement in Calculus 1, except we now know that it's not just a constant vector. Otherwise, there is no difference. Yeah, so similar, just quickly review something that we saw some time ago. If my acceleration vector is 0, negative g, remember that one, right? So free fall, and then I can do anti-differentiation to get my velocity, and I will have to, once again, all I have to do when there is no specificity to initial conditions, then I integrate this thing, so it will be component-wise to get from velocity to acceleration. So a prime is equal to, v is equal to a, v prime is equal to a, okay? And so I'm doing anti-differentiation component-wise, and only at the very end, so it will be t here, and a 1 here. No, it will be 0, and negative gt plus c. So that c is a vector. You don't have to also anymore split it between different things. And if I want, instead of 2 dimensions, I have 3 dimensions. It will be just the only difference will be that it is a 3-dimensional vector. Okay, and furthermore now I go locations, and p prime is equal to v. Okay, so then the next step is do another anti-differentiation, and it will be p is equal to integrate whatever necessary component-wise. So I'm going to still have 0, right? Negative gt integrated component-wise will be negative gt squared over 2 plus what? No, not c. ct, right? And there is really nothing special about it. It's c is a constant vector. We multiply it by a scalar, so it's just a scalar of our vector c, whatever that is, and then n plus say d, another constant vector. So, and we can now identify these specifically as these two. What's the meaning of these two vectors?
The initial position and initial
Initial, yeah. So initial velocity and initial position. Okay, so there we go. So that becomes very compact. If I'm willing to, I could insert. So I didn't really tell which one is x, y, and which one is z. So I could just as well insert y, say like this. So there is, once again, there is a y is pointing in that direction. So it will look like this, right? So adding the third dimension would have no trouble whatsoever. Integration will look exactly the same. All the vectors will be simply 3-dimensional vectors, and that's all there is. Okay. Okay, well, the fundamental theorem of calculus, probably we should state it at least. Fundamental theorem of calculus. Whichever version you prefer. Oh, do you remember the formula? So it's always very easy to remember the formula, and then you can figure out the conditions. But you should, but it's maybe backwards, but it's still better than nothing. So what's the formula?
Integral of a from A to B.
Say, I put F here to emphasize that once again we're talking about parametric curves. What is equal to
FA minus FB.
no, not F, right? So
F
since
of-
it's a different function, unless you want to put F prime there. So so I just put G of B minus G of A where what's the relation between F and G?
G is the
G is the antiderivative of any antiderivative of F. In other words, simply F prime is equal to G. Then all you have to do in order to have the conditions worked out is that F would have to be continuous. So you start the theorem by stating so that hold on a second, I got it all wrong here. It's the opposite. G prime is equal to F. Okay, so the only condition then is whatever is what we need to require in order to the expression itself to make sense, and that is the continuity of F. We didn't really discuss that either whenever a function is integrable, but once again, I refer you to component-wise approach, and so if you can, if every component of the parametric function is continuous, then it can be integrated component-wise, and we have the whole thing ready to go. So suppose F is continuous, then we have this conclusion, which is also the interpretation is a motion-wise interpretation is F is our velocity changing continuously, and then if we integrate the velocity from point to point of time, then the result is, if I integrate the velocity over a period of time from A to B, what's the result?
Displacement.
That's right, total displacement. So this is the interval time. So this is the total displacement over the period AB, or period of time AB. So that's where you are in the beginning, and this is where you are at the end. Okay. So two locations. Let me just see the difference. Yeah. So like F of A, and then whatever has happened. The function itself might behave wildly, but we will only know where we were in the beginning and then we were at the end. Okay, so everything, as you can see, have reappeared. What did not, and really does not reappear from calculus 1 is things about extreme points. So maximum, minimum, there is no such thing. And on the plane, in what sense can you think about maximum, minimum points? It's not that simple. Now I want to have an example more about n-dimensional situation. And suppose in n equal 2, it's a circle. It's very simple, and but if n is higher than 2, then it's n equal to 3 is a sphere. then you realize that the room, you have much more room to move. If it is a circle, it is a circle. You might try to move back and forth, slow and faster, but it's still not a lot of room in comparison to if you have a sphere. You can actually move in an arbitrary way like this. So that's what I'm talking about. We're talking about on, well, I guess I should write out, this is what I was talking about. Okay, so the magnitude of, that's actually a location. Okay, and suppose your, all right, let me put F here. F of t. So F is your location, t is time, and suppose your distance to the center to the origin here remains the same. Okay, so once again, that's the only condition. The only condition is that we are not moving away, no closer, no farther away from the origin. So it is once again in dimension 2 the circular motion. In dimension 3, we cannot even say what that is because it can move back and forth and making circles on the sphere. So you're like traveling on the surface of the Earth. So then it appears that it is very little we can derive from it, but turns out that we could. So what do we know about it? And a very interesting computation is just to look at this. And look at, so by it I mean f prime. So what do we know about f prime? In other words, the velocity. Your location is f prime is the velocity. What do we know about f prime? And it seems like we don't know a lot looking at that picture over there. But let's carry out let's look at the square of the magnitude. Well, I'm running out of time, so we'll do it next time. Okay.